this is the 8th symposium. We have already conducted this symposium 7 times from India, from Taiwan, as our invited speaker from Australia, and also many countries. Now we conduct this symposium from the speaker from the Egypt. International Symposium is a series of our program, a platform for authors who have published articles in Teknomekanik Journal to disseminate their research results, engage in discussion, and collaborate with other researchers in the scientific community. Okay, ladies and gentlemen, before our speaker present his article, Mr. Ghazy, I would like to invite Mr. Aprila Fortuna from Editorial Office and also an alumni of Universitas Negeri Padang present an overview and insight of Universitas Negeri Padang and our lovely place, West Sumatra. Please, Mr. April, time is yours.
Okay.
Maybe some interruption. Hope you are waiting. Is there any problem, Mr. April?
Yes. I think I have a technical problem.
We are sorry. Sometimes it happen out of our expectation. Please, Sir April.
Okay, hello everyone. First of all, I'm so sorry. We have a technical problem to share screen our PowerPoint. So, good afternoon, everyone. I hope you are doing well today. My name is April. I was a student from Universitas Negeri Padang. I'm honored to be here today at Teknomekanik International Symposium. It's a great opportunity to me to briefly introduce our university, Universitas Negeri Padang, and you can say UNP for short. UNP is a publicly university based in Padang City, West Sumatra, Indonesia. We started back in 1954 as a teacher education college in Batu Sangkar, and after that become Universitas Negeri Padang in 1999. Today, UNP is ranked among the top 25 university in Indonesia. We have some achievement, and we have some uh, uh, faculties which include Faculty of Engineering, Faculty of Education, Faculty of Language and Arts, and we have a lot of faculty here, like vocational school, postgraduate school. So our programs are accredited by prestigious international agency like ASIN, AKAS, and AUNKIE. So let me share a little bit about Universitas Negeri Padang. Next slide. Next. Please, Doctor, next slide to.
Okay, wait, I'm sorry. I also have the problem.
Oh, I don't mind.
Okay, wait. Is it possible visible now?
Yes.
Next slide.
Yes. Next slide. Slide 3. Okay.
This one.
Yeah, this one. Okay. Okay, let me share a little bit about Universitas Negeri Padang and Sumatera, West Sumatra with all of you today. Research excellence at UNP is prone to be Q1 in research within Indonesia, and we are in 26th position nationwide in EDN 2025 in this Chimago research ranking, and this shows our strong commitment to get a higher ranking in the next year. WINP offer a world-class campus that include the Rectorate Research and Centers, the Baganjong Rectorate Building, and our integrated laboratory supporting cutting-edge research in various fields. So if you come to Padang, you will explore the beautiful landscape my home our institutions. So Indonesia most breathtaking destination for you, like Mentawai Island, Mandeh Tourism, Harau Valley, and our and Rumah Gadang Paguriyong. And then next slide, beside our academic strengths, University Padang is located one of the most beautiful spots in Indonesia, West Sumatra. So next slide. Yeah, belum. Yeah. Okay. The last but not least is the last but not least, beside our academic strength, you can find many destinations to uh, Padang City. As you can see from this image, West Sumatra is filled with a rich culture heritage, stunning landscape, and world-class tourism in Indonesia. From the iconic Rumah Gadang, the traditional Minangkabau house, to breathtaking place like Maninjau, like Singkara, and the Mentawai Island. This region is perfect to everyone who want to mix academic with culture and nature. Yes. So if you have opportunity to come Padang City, you can find many destination like this image. We truly believe that being this environment not only support excellent learning, but also helps this personal enrichment. And yeah, thank you so much today, and I hope you all well-being.
Okay, thank you very much, Mr. April, to give the overview and all insight of our university and also our lovely place, West Sumatra, especially Padang. University Negeri Padang is located in Padang. Okay, ladies and gentlemen, before our speaker present his article also, and I would like to give the short information about our speakers. Before we proceed to the presentation of Mohamed, Mr. Ghazy, you cannot love what you don't know, can't you? So, what is the Teknomekanik? Is there any interested program organized by our journal? Does Teknomekanik only publish an article? Is there any program? Okay. Keep all your curiosity and also all the question. Now, I would like to introduce our journal, Teknomekanik. Have you know our Teknomekanik website? You can access in the website www.teknomekanik.unp.ppg.ac.id. Okay. This is our website. You can find in this website teknomekanik.ppg.unp.ac.id. All the information about the Teknomekanik is provided by the website, including the submitting your manuscript. Currently, Teknomekanik is a quartile hitus, Simago, and Scopus stat score 2.2. This one. Okay. And now we are happy to inform you that we are in the preparation to be included in the Web of Science Index. I hope we can process this proposal to the Web of Science. And all the highly qualified and impact manuscript within the scope of the mechanical, chemical, ocean, electrical, and electronic engineering, including the engineering miscellaneous, are welcome to submit to our journal. Now, starting from the 2026, next year, Teknomekanik will publish 3 issues a year, January, May, and September. Previously and currently, we already publish 2 issues in a year, June and December. For the Sir Mohamed Ghazy article has been published in our issue in June. So you can access the articles of Mr. Ghazy in this issue. Starting from the next year, we will publish 3 issues in a year, covering 10 to 15 articles. So you have more opportunities to publish with us. Regarding our program or event, in this website, you can also find our other event. Except International Symposium is only one event of our program. We also have a roadshow and journal managerial session. Maybe the admin can show the Teknomekanik event. Not only this symposium, we also have the roadshow. What is the roadshow? Roadshow is also this one. This one is roadshow. So in the roadshow, the editorial team will offer a workshop on academic writing and publishing to any institution or university that is interested to be hosting in this event. Any inquiries and also the information about the Teknomekanik Roadshow you can find in our website. Any inquiries, you can send an official letter to our email. We already conducted this roadshow in Yangon Technological University, Myanmar, and also some of the journal in Indonesia that already Scopus index now. We are happy to share our knowledge in journal managerial session and also academic writing from our editorial board. This one is one of the roadshow and also the managerial session. Also, the trainer in this managerial session. This one, our editor-in-chief, Mr. Rahmat Aziz Nabawi, will share his experiences in a journal managerial session. He also already conducted all the managerial session in many universities in Indonesia. Okay, ladies and gentlemen, I hope this little or short information about our Teknomekanik and also the program. If you're interested, you can contact us officially from the by the email. We move to next session, presentation from our invited speaker, Mr. Ghazy. Keep your question until we are in the Q&A session. However, before the presentation, let me introduce to you our speaker, Mr. Ghazy. Currently, Mr. Ghazy enrolled in PhD program in Applied Mathematics, Faculty of Science, Al-Azhar University, Cairo, Egypt. So does his master in science in the same faculty and university. He is also mathematics teaching assistant in the Faculty of Engineering, German International University. Please welcome our speaker, Mr. Ghazy, to present his topic, the impact of exponentially varying viscosity or magnetized tangent hyperbolic nanofluid over a nonlinear stretching sheet with PHF and PMF condition. Please, Mr. Ghazy, enjoy your time. Time is yours now.
Okay, thank you, Dr. Shadi. Hello, everyone. Good morning to everyone here in Egypt, and good afternoon to our participants in Indonesia. Thank you for joining my talk today. I'm Dr. Mohamed Magdy Ghazy, Assistant Lecturer at the German International University in Cairo. This presentation is on behalf of all co-authors, Professor Dr. Khalid Mekhemer and Associate Professor Rabia Abul Khair and Professor Ahmed Mustafa Mujahid. The work I will present titled The Impact of Exponentially Varying Viscosity on Magnetized Tangent Hyperbolic Nanofluid over a Nonlinear Stretching Sheet with Prescribed Heat Flux and Prescribed Mass Conditions. This outlines number 1, introduction and the research gap. Number 2, mathematical model and formulation. Number 3, numerical solution method. Number 4, results and discussion. Number 5, conclusions. Number 6, future work. The work I will present titled was published in Teknomekanik, Volume 8, H1, with valuable guidance from Editor-in-Chief Dr. Rahmat Aziz. Number 1, let's go to the next slide. We address a critical problem. Cooling of high heat electronic components requires efficient nanofluid-based heat transfer. However, prior to research has significant gap. It hasn't simultaneously modeled the combined effect of exponentially varying viscosity or magnetic fields and prescribed exponential order heat flux and prescribed mass flux boundary conditions. K nanoparticles phenomena, interplay of Brownian motion and thermoforces parameter and suction or injection in non-Newtonian nanofluid. To bridge this gap, our study investigates the flow and heat transfer of a tangent hyperbolic nanofluid over a nonlinear exponentially stretching sheet, incorporating all the above complex interacting factors for the first time. Let's go to the next slide. This is K innovations. Our K innovation are using tangent hyperbolic nanofluid, shear thinning behavior. Number 2, introducing on exponentially temperature-dependent viscosity. Mu equal mu naught e power negative beta 1 theta of eta, such that in mu is a variable viscosity. Number 2, boundary condition, prescribed heat flux, negative K partial T by partial Y equal TW minus T infinity e power X over TL. Prescribed mass flux, negative K partial T by partial Y equal TW minus T infinity e power X over TL. I will show difference between prescribed heat flux, and prescribed mass flux. The definition of prescribed heat flux is a heat transfer at the boundary. Physical meaning, fixed heat flow rate into or out of the system. Prescribed mass flux is a definition of prescribed mass flux, nanoparticle transfer at the boundary. Physical meaning, fixed nanoparticles mass flow rate into or out of the system. Number 3, magnetohydrodynamics effects, transfers, magnetic field, B equal P node E power X over 2L. Next slides. This slide will talk about types of fluids. We have types of two fluids. This slide explains the fundamental difference between Newtonian and non-Newtonian fluids, focusing on how they respond to applied force, shear stress. Number 1, non-Newtonian fluids have a constant viscosity. Number 2, the shear stress has a linear relationship with the shear rate. Example, common fluid, water, air, alcohol. Number 2, non-Newtonian fluid have a variable viscosity changed at under force. Number 2, the shear stress has a nonlinear relationship with the shear rate. Examples, blood, ketchup, paints. Subtypes of non-Newtonian fluid, I have two types. We have two types, shear thinning and shear thickening. Shear thinning, viscosity decreases with increased shear rate. Example, paint, blood, ketchup. Shear thinning, viscosity increases with increased shear rate. Example, cornstarch in water. And this figure shows that classification graph. The graph visually classifies non-Newtonian fluids based on their flow curves, shear stress versus shear rate. X-axis, shear rate, represents how fast the fluid is being deformed. And y-axis, shear stress, represents the force required to achieve that deformation rate. Different curves show that different fluid behavior. Non-Newtonian plastic requires a minimum stress to start flowing. Once flowing, it might be shear thinning or linear Bingham plastic. Shear thinning curve bends downward and shear thickening curve bends upwards. Let's go to the next slide. Introduction to the hyperbolic model. Moving to the specific fluid model central to our study. In the start, the tangent hyperbolic model is a mathematical model describing a specific type of non-Newtonian fluid characterized by shear thinning pseudoplastic behavior. The pioneer on tangent hyperbolic fluid flow, particularly in the context of boundary layer flow over a stretching surface, is attributed to Sakidas 1961 and Kran 1970. Sakidas initially investigated the boundary layer flow over moving surface. Kran then extended this concept to describe the flow over a stretching surface with a linearly varying velocity. These early studies by Sakidas and Kran were foundational for later research on magnetohydrodynamic tangent hyperbolic fluid flow, which has significant applications in various engineering and manufacturing processes. After that, this is applications of tangent hyperbolic fluid. Polymer extrusion machine, and is a fundamental piece of equipment in plastics and rubber processing industries. It's used to produce continuous shapes like pipes, sheets, films, tubing, or plastic profiles. Number 2, blood flow in vessels. Number 3, heat exchanger. After that, introduction to nanofluid. Nanofluid consists of base fluids combined with nanoparticles like carpets, oxides, and metals that have genotypal interest owing to their improved heat transfer characteristic. HI the first mention of nanofluids in 1995. Scientists and engineers can now conduct study in a new field thanks to this trial. Buongiorno 2008 discovered nanofluid application for nuclear reactors, and they made the argument that nanofluids are more advantageous economical and for nuclear reactor safety than their base fluid counterparts. One of the earliest research to introduce the concept of nanofluids and their potential for enhanced heat transfer was Dr. Echai. In 1995, while working at Argonne National Laboratory, he and his colleague John Eastman 2001 coined the term nanofluid to describe fluids containing nanoparticles that exhibit superior thermal properties compared to their base fluids. While Echai initial work focused on the general concept of nanofluids, subsequent research expanded to include non-Newtonian nanofluids, which are fluids that don't follow Newton's law of viscosity and contain nanoparticles. Next slide. This application of nanofluids: number one, solar thermal collector with nanofluid. Number two, nuclear reactor cooling. Number three, biomedical hyperthermia treatment. The mathematical model and formulation. Physical model description. We model a steady and incompressible and two-dimensional tangent hyperbolic nanofluid. Number two, exponentially nonlinear stretching sheet with velocity at the wall UW equal A node E power X over L. Number three, a variable transverse magnetic field B equal B node E power X over TL to L is applied along the y-axis. Viscosity varies the temperature mu equal mu node E power negative beta 1 theta over eta. After that, and this sketch of physical problem, x-axis and y-axis, such that x-axis is a stretching sheet and y-axis is perpendicular over x-axis. Governing equation. The first equation represents a continuity equation. Number two, momentum equation. In the momentum equation, left-hand side represent a convection acceleration or inertia forces. Right-hand side, first term, linear viscous term, and second term represent a nonlinear term. Together, these model the tangent hyperbolic fluid behavior. Number three, energy equation. The left-hand side of energy equation represent a thermal convection. Right-hand side, this first term, dB partial C by partial Y, partial T by partial Y, this represent a Brownian diffusion. Second term, thermoforces, nanoparticle move from hot to cold, carrying heat. Last term, alpha partial square T by partial Y square, this represent thermal diffusion or conduction. Last equation, concentration equation. The left-hand side is a represent nanoparticle convection or transport by fluid flow. Right-hand side, the first term, dB partial square C by partial Y squared, this represent Brownian diffusion or spreading of nanoparticles. dt over T infinity partial square T by partial Y squared, thermophotic diffusion. After that, we assume the boundary conditions. U equal UW, E node E power X over LL. This boundary condition where U and V are velocity component in the X-axis and Y-axis directions, respectively, such that in UW is velocity at the wall and VW represents the velocity of suction or injection. And sigma is fluid conductivity, and P naught for magnetic field strength, T temperature, Cb specific heat at constant pressure, rho is fluid density, Bu is coefficient of fluid density, E naught denotes the rate of stretching surface, and this term is very important. After that, N is power law index, and this term represent hypertangent nanofluid. Gamma is positive time constant, dB is Brownian diffusion coefficient, and dt is Morphosis diffusion coefficient. K thermal conductivity, and alpha is thermal diffusivity. The dimensionless. Purpose of dimensionless transformation. To solve our complex coupled partial differential equation, we transform them into dimensionless form. This a dimensionless variables. And this a dimensionless mu equal mu naught e power negative beta 1 theta over eta. Such that in general, if لو beta 1 greater than 0 for liquids and beta 1 less than 0 for gases and beta 1 equals 0 for constant viscosity. And this dimensionless for each term u, v, eta, t, and c. After that, after transformation, the governing equation reduces to first equation represent the velocity equation. Equation number 2 represent temperature. Number 3 represent a concentration equation. And also transformed boundary condition are then given by at eta equal 0 and eta equal infinity. We have two walls, x-axis and y-axis. X-axis at eta equal 0, y-axis at eta equal infinity. And these parameters after dimensionless. First parameter represent a Weisenberg number. Second parameter, magnetic field, and LS is suction or injection parameter. SC is a represent Schmidt number. NP is a represent Brownian motion and thermoforces parameter, and Prandtl number. After that, this slide will talk about a numerical solution method. We used a Chebyshev spectral method. A Chebyshev spectral method is a numerical technique used to approximate the solution of differential equation, ordinary or partial, by expressing the unknown solution as finite sum of Chebyshev polynomials. Mathematically, the method represents the solution u of x as u of x equal summation k equals 0 to n a index k and times t index k of x. T index k are Chebyshev polynomials of the first kind. A index k are the coefficient to be determined. And n is a degree of truncation, number of modes used. K ideas. The domain, usually from -1 to 1, is discretized at the Chebyshev-Gauss-Lopatto points for better numerical stability. Number 2, differentiation matrices built from Chebyshev polynomials are used to approximate derivatives efficiently, particularly powerful for smooth problems due to high accuracy with relatively few grid points. Example use: solving boundary value problems, solving eigenvalue problems, fluid dynamics, simulation heat transfer models. After that, there is a slide show that how the Chebyshev spectral method differs from other numerical methods. Chebyshev spectral method uses global Chebyshev polynomial over the entire domain, and very high accuracy and fast convergence, excellent for boundary layer problems if the solution is smooth. Best for simple domains like intervals and rectangles. Work on non-uniform grids, Chebyshev point clustered near boundaries. Other methods like finite difference and finite element methods use local approximations, low accuracy per node, conversions is slower, suitable for complex geometries, usually based on uniform or structured meshes, but can handle unstructured mesh finite element method. Regarding the equation and their implements in Mathematica, they can be found in the published paper in page number 8. After that, Numerical solution method. The numerical workflow is summarized as follows. Start, initialize the boundary value problem derived from the transform ODEs. Number 2, boundary value problem, define boundary condition for the exponential stretching sheet. The Chebyshev spectral method. Number 1, I will transform a domain from 0 to infinity, convert to -1 to 1 via algebraic mapping. Discretize using a Chebyshev collection point on from -1 to 1. Convert the ordinary differential equation into algebraic equations via spectral differentiation matrices. Solving. Solve a system iteratively in Mathematica and extract solution, velocity profiles, and shear stress and validate against benchmark. And regarding the equations and their implementation in Mathematica, they can be found in the published paper in Teknomekanics on page number 8. After that, results and discussion. The validation. This table shows that results comparison of f double dash of 0 for various values of magnetic field when Weisenberg equal power law index equal suction or injection parameter or variable viscosity equal 0. And this is a special case of this model. We note that a strong agreement with present result. The present result is very strong agreement with Akbar et al. 2015 and Amgad et al. 2023 in table 1. And we note that these studies were selected because they investigate the same time of boundary layer flow and employ similar simplifying assumptions, allowing for consistent and meaningful comparison. Akbar's study examines the effect of magnetic field on ring bowel fluid flow over linearly stretching sheet, while Amgad explored tangent hyperbolic nanofluid flow over an exponential stretched sheet with prescribed exponential order, surface temperature, and heat flux conditions. After that, this slide shows that the data obtained from Mathematica code. Number 1, this is a velocity profiles. Figure from 3A and 3D displays the impact of velocity profile versus on beta 1 and N, the effect of beta 1 on the velocity F dash are depicted in displayed figure 3A. As beta 1 increase, and overall velocity profile decreases, a result of larger temperature gradient between the surface and ambient fluid. Moreover, for beta 1 greater than 0, the velocity near the wall flattens more rapidly than in the Newton case beta 1 equals 0, indicating that the non-Newtonian tangent hyperbolic behavior further reduces flow resistance. And in figure 3b, the effect of power law index on F dash is shown graphically in figure 3b. It's obvious that when n grows, the velocity profile falls. From a physical standpoint, its influence on the fluid's rheological characteristic is what is responsible for the drop in velocity distribution. Linked to a raised power law index parameter, physically, the fluid's reaction to shear stress is primarily responsible for the decrease in nanofluid velocity. Velocity linked to the power law index, and fluid velocity decreases when the power law index rises, indicating increased resistance to shear. After that, and this figure is depicted in figure 3c that a reduction in the velocity profile as the value of magnetic parameter rises, according to the retarding force causes. In a physical sense, the magnetic parameter rises. So does the Lorentz force applied to the fluid. As a result, the fluid moves more slowly as a result of the decreased fluid velocity. And in figure 3D, the effect of suction and injection parameter S is depicted in figure 3D, where the velocity profile grows with increasing for suction or injection parameter. We interpret physically while the velocity profile grows with increased suction, it reduces with increased injection. The reason for this is that when the fluid injected into the system close to the surface, it takes up space next to the wall, increasing the momentum boundary layer thickness. Number two, in section case, the fluid in the surrounding area of the surface moves out, which complicates the formation of the boundary layer. Consequently, the immediate effect is the injection on the suction is they that change and decrease the boundary layer thickness for the velocity profile. Let's go to the next slide. And the next slide shows that temperature profiles. The influence of beta 1 on temperature versus eta is shown in figure 4a. It has been noticed that an rises in the fluid viscosity parameter beta 1 tends to an increase in thermal boundary layer thickness. As a result, theta of eta value rises. Consequently, a rise in beta 1 raises the fluid temperature. The temperature variation for power law index is displayed in figure 4b, where the temperature is increased. Physically, a rise in Ln or power law index causes a rise in viscosity. As a result of a surge in viscosity, the fluid temperature rises. After that, figure 4c and figure 4d presents the impact of magnetic parameter and suction or injection parameter S on theta over eta. These figures conclude that the temperature grows for larger value of magnetic field parameter and suction or injection parameter. Physically, for this figure, for magnetic field parameter, the idea is that when the magnetic parameter increases, the Lorentz force is created and friction is created on the fluid. Friction increases the amount of heat energy produced, which in turn raises the temperature profile in the fluid. After that, the figure for A and figure for F display the variation of NT and NB for theta over eta. Both the temperature and corresponding layer thickness except similar behavior for larger NT. We increase the thermoforces parameter. We conclude that fluid particles rise from the system hot to cold regions. It results from a rise in the thermoforces force, which raises the temperature profile. Refer to figure 4e. As NB increases is estimated higher, the temperature rises due to enhanced random motion of the liquid particles. And this slide, concentration profiles. The impact of beta 1 and N and S and NT on G of eta, and G of eta represent a concentration or mass transfer, is depicted in figure from 5A to D. Concentration profiles grow for larger values of beta 1 or N and S. And additionally, and N raise in thermophotic parameters, NT was shown to enhance the concentration levels. And also, this profiles when a change increased suction or injection parameter, this we conclude that the mass transfer is increased and thermoforces parameter also increased. Why? Physically, when the thermoforces parameter NT as shown the main component as a result of nanoparticle resistance to heated surface during thermoforces process. They scattered from the warm surface into surrounding fluid in this manner. In this manner, the thermophotic force is responsible for the transfer of heat from the surface to the flowing fluid through nanoparticle, and there interpret for thermophotic parameter. After that, the behavior of Brownian parameter on G of eta is depicted in figure 5e. A reduction in concentration of nanoparticles results from raising Brownian motion. Due to Brownian motion pushes the particles outside of the fluid system as the boundary layer warms. As a result, as particle size decreases, nanoparticle mobility increases and thermal conduction is improved as NB increases. Physically, the main component of nanofluid is a two-phase system where the kinetic energy is increased by the arbitrary motion of the nanoparticles. However, Brownian motion has a significant impact on the diffusion of nanoparticles. When Brownian motion is present, the concentration boundary layer thickness decreases. And we all know that. Last graph, 5F. 5F shows that the variation of Schmidt number on G of eta. There is a diminishing effect as SC values increases. As Schmidt number rises, the concentration boundary layer thickness reduces because of a decrease in mass divisivity. After that, this is a conclusion of this papers. In this work, analyzed the numerical solution of the variable fluid viscosity on magnetohydrodynamic Newtonian nanofluid of variable viscosity with prescribed exponential order heat and mass flux through an exponentially stretching surface using proper similarity transformation. The governing equation of nonlinear partial differential equation is converted into the system of nonlinear ordinary differential equations. The transformed system of middle equations was solved using Chebyshev spectral method. There was a strong agreement between our findings and those from previously published works. The flow and heat transfer details are highlighted by numerical results. Are shown in tabular and graphically. These are the model's most significant outcomes listed in order importance. The rate of a change of the velocity, temperature, and concentration profiles have a term which is directly proportional to viscosity beta 1 not equal 0 than constant viscosity beta 1 equal 0. The velocity and temperature profile will rises with increase of suction or injection parameter. The rising in the Schmidt number causes and reduces in the concentration profile G of eta, while enhanced in the case of beta 1 not equal 0 and the power law index not equal 0 and the suction or injection parameter not equal 0 and thermophotic force not equal 0. After that, the future work extend to unsteady flows or 3D models, include thermal radiation or slip effects and porous media. Unsteady nonlinear stretching, also dual solution and stability analysis, hybrid nanofluids, and last, experimental validation. Acknowledgement. I would like to express my sincere gratitude to the co-authors of this work, Professor Khalid Mohamed, Associate Professor Rabia Abul Khair, and Professor Ahmed Mustafa Mujahid for their valuable contribution and collaboration. I would especially like to thank Professor Khalid Saad Mohamed for his continuous encouragement and support, particularly in motivating me to participate in this symposium. I would like to thank my professor at Al-Azhar University and my colleagues at the German International University for attending this symposium and for their continuous support. I also extend my appreciation to Associate Professor Rahmat Aziz Nabawi and the editor-in-chief of Teknomekanik for his invaluable guidance, and to Associate Professor Sri Rizeki for his excellent moderation during the symposium. Thank you for your attention. I now welcome any question you may have.
Alhamdulillahirrahmanirrahim. Thank you very much, Mr. Ghazy, for the great presentation and also for sharing your experiment and also your study. Okay, ladies and gentlemen, now we are in the Q&A session. If anyone wants to question, please raise your hand and also unmute your speaker. Anyone from the floor wants to ask the question? We have the lecturer from our university, in our department and also from our faculty. We have the faculty of engineering here. From department mining, mechanical, automotive, civil. Anyone from the floor wants to ask the question? Anyone? Maybe there are participants from the mathematics, natural science. Anyone? Okay. Maybe also from the Egypt, from your university, from your friend.
The
Is there
friend
any friends from your lab, Mr. Ghazy?
the friend is my is your like me and wants to ask questions.
So this is part of your PhD study,
Yes.
Mr. Ghazy? Oh, okay.
Okay.
I saw your result section is rich with the graphical data. Actually, this is perfect for the interpretation question. I saw in your previous slide, your figure 3C and the 3D. Can you open the slide?
Okay. 3C and 3D. Yes.
Okay. Maybe your professor wants to ask the question.
Okay.
I saw
No,
in
I
your.
just- I would like to thank Mohamed Ghazy for his presentation. It's well good students. And as you say, we wait for a question from the audience. That's all.
Okay,
Thank you.
okay, Professor McMamer. Is it correct? Your name, Professor?
Yes,
I'm sorry if
Mekhamer
I
or
press your name
Mekhamer.
correct.
Yes,
Dr.
yes.
McMamer. So from your figure, 3C and 3C and the 3D, please describe the impact of the increasing the magnetic parameters and the suction injection parameter S on the fluid velocity profile. Please explain the physical reason for this effect of M.
Okay. Is this a suction parameter? Yes.
Yeah, this figure.
Okay. Basically, while the velocity profile grows with increased suction, it reduces with increased injection. The reason for that is that when the fluid is injected into the system close to the surface, it takes up space next to the wall, increasing the momentum boundary layer thickness. In a suction case, the fluid in the surrounding area of the surface moves out, which complicates the formation of the boundary layer. Consequently, the immediate effects of the injection and suction is that they change and decrease the boundary layer thickness for the velocity profiles. Just all.
Okay, thank you very much for your answer. This your study focus on the boundary layer, is it right?
Yes.
Okay, maybe some of the participants lost the information. Could you explain or describe again what is the PHF and the PFM boundary condition? So if you want to follow your study, we should also focus on your boundary condition.
Okay.
Can you explain about the boundary condition that you take into the
After
consideration
boundary condition
of
after
your study?
similarity or before similarity?
Pardon?
We introduce the boundary condition after similarity or
Yeah.
before similarity?
Before and after?
Just mention the physical meaning for these two boundary conditions.
This one. Maybe the boundary condition. Maybe some of the participant hasn't read the article yet. In the article, you have mentioned, describe it in the method.
Yes.
Maybe you can highlight in this symposium about the boundary condition, taking
Okay.
into the consideration in the study.
Okay.
This one, the boundary condition.
Boundary condition such that U equal UW equal A node E bar X over L, such that is a velocity in the X directions, and the X axis happen to stretching sheet, but V equal VW equal negative gamma over X equal negative V node E bar X over 2L. This is a velocity of suction or injection, and in the Y axis, suction or injection in the direction or along in the y-axis. And after that, prescribed heat flux and the prescribed mass flux. Prescribed heat flux and the prescribed mass flux. Okay. With respect
Thank you
to
very much.
Okay.
So this is the boundary condition. I hope the participant can understand and also following your study. Okay, I have the note from the luring participant. Oh, this one for the opening. I'm sorry. About the potential collaboration with us in Universitas Negeri Padang and your university.
Okay.
We will talking about it later.
Yes, sorry. Sorry again.
Okay. Anyone wants to ask the question? Anyone?
Okay, I think there is no questions and
Okay. I think no question anymore.
yes.
And also, this article has been published, as I stated before, I informed you before, this article already published in our current issue in June. So you can access our open journal. It is free for the readers. This article is open journal, open system in your in this journal. So you can access and also you can check these articles and other relevant article to your study. Thank you very much, Mr. Ghazy, for your great presentation and sharing your study.
You are
Now,
welcome. You are
The
welcome.
journal, I want to say that a journal is indexed in Scopus for this year,
yes. If
2025.
you see in the if you see in the Scopus into the 2025 still
Okay.
index in the Scopus. In the Scopus we are the quartile 3 Q3, but in the Simago we are the Q2
Q2, yes.
percentile. In the Scopus we have the percentile 2.2.
Okay. More
This
success
is
for
the
journal,
article, your
I think.
article.
Yes.
Amin, inshallah.
Wish you more
And I
success for
hope,
journal, okay? I wish more success
inshallah,
for
because
journal.
we are already,
Inshallah. Inshallah.
we are
Yes.
preparing to submit to the WAS
Okay.
this year, inshallah.
Inshallah.
Okay,
Thank you very much.
if no a question anymore, is it a happiness to have you with us, sir, and also the professor. We would like to thank to you for your contribution in our event and our journal. We wish that we have the collaboration between our university, as I mentioned before, Universitas Negeri Padang, and your university, maybe such as a research collaboration, study exchange, and other academic program. For the certificate, we will send to you, Mr. Ghazy, and for the participant, we will send the certificate by your email.
Okay, thank you very much, Dr. Sri.
Okay, thank you very much also. We also want to appreciate Yeah, for the Scopus index, your article will appear in the Scopus index within 4 to 6 weeks after the publish. So in the next 4 to 6 weeks, your article will be indexed by the Scopus.
Okay, I can see that. Thank you very much.
Oh, okay. Okay, you are welcome.
Thank
We also would like to appreciate all the audience for the active participation in this event. We apologize, very sorry if there any leaking in our event, especially the technical problem that happened in the beginning of this symposium. Hopefully, this symposium will be beneficial for everyone. Alhamdulillahirabbil alamin. Finally, it's the end of our symposium. Thank you all, Professor, Mr., and also all the participants to joining this event, this symposium. Thank you all, and see you in the next symposium and other events. Greeting from us, from our editorial office. Assalamualaikum warahmatullahi wabarakatuh. See you in the next
Waalaikumsalam warahmatullahi wabarakatuh.
Terima kasih semuanya. Assalamualaikum warahmatullahi wabarakatuh.
Waalaikumsalam warahmatullahi wabarakatuh.